Hi there, this is MG5004 DE5418, topic 10, class 1, where we look at integration. This is matched by chapter 17 of your textbook, where we look at integration, basic ideas of integration, definitions, and definite and indefinite integrals. Most of you at this stage will have already met integration in the same way as you'd already met differentiation. With differentiation, we start with a function and we proceed to find the derivative. With integration, we start with the derivative and work backwards to find the original function. However, without knowing the part of the history of the function, there might have been a constant term that differentiated away to 0 and all trace of it in the derivative is gone. So all we can do there is to indicate that there might have been one by using C or K or some other constant. It's vitally important that we include it. Lots of physical interpretations exist for integration. We will look at some in class 1 and we will look at some in class 2 as well. Things like area under a curve, area under a velocity curve, area under a current curve is the charge, and so on. But it's much more than simply differentiation in reverse. It's necessary to regard integration as a process of adding up the little bits. Now you remember differentiation is all about the limit as delta x tends towards 0. It's the same thing here. We're adding up. If we've got lots of little bits that we want to add up, say like this, then if we made these bits smaller and smaller, so if that was delta x, if we made delta x tend towards 0, then eventually we'd get a curve with teeny tiny bits underneath it. So it's adding up lots of little bits. So it's about summation of tiny bits. So, for example, the position of the center of mass of a solid body can be found by adding up all the little parts from which the body is composed. And as the parts get smaller, as delta x or delta t tends to 0, then we get into the idea that we're adding infinitely small pieces. And so as our rectangles in here get smaller and smaller and smaller, our area would be more and more accurate, and there'd be less kind of bits left over in here. So it's all about, again, delta x and delta x tending towards 0. We need to just check that you remember all the right words. The squiggle at the front is the integral sign. The integrand is what we are integrating. The dx bit here, this is a bit that's a bit confusing, but it indicates the name of the variable that we're integrating with respect to, in the same way as dy by dx. We talk about dx. It's indicative of the variable. Now here on the previous slide I mentioned that we needed to add in this constant because it might have been something like x squared plus 4 that we differentiated away the constant. If we have a look at, say, x cubed plus 4, x cubed plus 17, x cubed minus 24, all of those differentiate to 3x squared. So the integral of 3x squared with respect to x could be any of those. So the best we can say is it's equal to x cubed plus some unknown constant. There are rules. I'm not sure that that's quite the right page for your textbook, but there is a list in your textbook of common integrals. There'll be a list in any textbook on common integrals. So this is the most common rule, the power rule. And if we're going to integrate a sum, we just integrate from left to right. If we have a number here times a function, then our integral, we can take the number out the front. We're only integrating the xy bits, right? We're only integrating the bits that are related to x. So we could add the derivatives of the integrals of a sum, and again we could put the number out the front. Often there's no strict rules for this fits all. Sometimes we have to do a bit of trial and error. There's certainly no straightforward rule for the integration of products and quotients as there was for differentiation. We do have to use integration by parts, which we'll cover later on. Again, I'm not sure that's the right figure, but it doesn't matter. Here's a list of standard integrations. It's a small one. Sometimes it's helpful if we actually learn them, but you're not expected to learn them. You will be given a list. You're allowed to use your e-text anyway in the exam, and you will be given a list that you will need, of the ones that you need. Where we've got some functions where clearly we're talking about inverse functions, then there's a special rule to integrate those, and then it's just a matter of deciding which to call x and which to call y. In this first example here, if y is equal to inverse cos of x, then x is equal to cos y. So then we can say, well, the integral of the inverse cos of x is going to be, just using the formula, xy minus the integral. So then this bit must be what we're talking about here. This bit must be cos y, and we know that the integral of cos y dy would be sine y plus some constant. So that's just from the list. Now that's fine, but it's not very polite. So we need to replace the y's back into terms of x. So x, well, we know that y was cos inverse x, sorry. So I've done that bit. Now we need to find sine y. Okay, you know that sine squared y plus cos squared y must be equal to 1, and we could rearrange that. So sine squared y equals 1 minus cos squared y. So sine y equals the square root of 1 minus cos squared y. Now think of your ordinary triangle, unit circle type triangle, where the hypotenuse is 1 and x is there. Then x is going to be equal to cos y. Putting y in the diagram there, x is equal to cos y. So now we can say that sine y is equal to 1 minus cos squared y, which would simply be x squared. Now that means that if we now replace sine y with the square root of 1 minus x squared, we're fine. Everything's back in terms of x. Don't forget, plus c. The integral of natural log x, you might actually know this when you've done it, but maybe not. So we can do the same thing, that if y is equal to the natural log of x, then x is equal to e to the y. And just thinking along a little bit further here, e to the y is equal to e to the natural log x, which equals x. Just hold that thought. So then the integral of natural log x dx is going to be equal to xy minus the integral of e to the y dy. And now we already know that the integral of e to the y will be e to the y. So it'll be xy minus e to the y plus c, but we know that e to the y is actually x from here, just from our rules of logs and things. So we can go straight away to say that that's x. Now y was natural log of x, so we can replace the y by natural log of x, and then this would just be e to the y is x. So you might already know that, otherwise it's one to learn. As I said at the start, there's no one rule fits all. You have to look at each case separately and go, which tool am I best to use here? For the first one on this slide, we would be looking at using a trig identity of the sort that sine A cos B is equal to a half sine A plus B plus sine A minus B. And you kind of get the idea to look at that, because look at the 2x and the 4x. You kind of have to have a feel for it. But once we've done the work on trig, which you did earlier on, we can say that this is equal to a half, just straight out by trig identity, sine 6x plus sine 2x dx. Now, using rules, that now becomes very easy. It's a half times the integral of sine 6x plus a half times the integral of sine 2x, which would be a half times a sixth times negative cos 6x plus, and it's going to end up minus because of the negative sign. The integral of sine is negative cos, so make it negative anyway. A half times a half cos 2x plus c. Tidying that up, that would give us negative a 12th cos 6x minus a quarter cos 2x, don't forget, plus c. Looking at the second problem, in your mind you should suddenly say, that reminds me of the work that we did on partial fractions, so we need to decompose this first. So we need to decompose 23 minus x over x minus 5 times x plus 4 into a over x minus 5 plus b over x plus 4. And from there, if you remember back to the work, we would get that a times x plus 4 b times x minus 5 will be equal to 23 minus x. Okay, trying if x equals negative 4, then b times negative 4 minus 5 would be negative 9 equals 23 minus minus, so that would be plus 4, so that would give us that b was equal to negative 3. Similarly, if x was equal to 5, then the second term disappears and a times 9 would equal 23 minus 5, which would be 18, so a must equal 2. So that means that our initial problem decomposes to the integral of 2 over x minus 5 from this term, now that we've found a, plus, except that it'll be minus because b is negative, the integral of 3 over x plus 4, and then it's just a log problem then. It's 2 times natural log of x minus 5, just from the table, minus 3 times natural log of x plus 4 plus c. Don't forget plus c. So look at it, decide what kind of problem it is, which rule you're going to use. There's no one rule. You have to look at each case by case and work out what to do. Again, I'm not sure that's page 795, but there are some special cases, and it's a matter of recognizing the special case and then just proceeding. These special cases will just be in a list. Again, more special cases. Look at it, find it in the list. There's your integral. Here we'll do some of the examples where you just need to find it in a list, find the appropriate format and recognize it, and then just do it. Now what I'm going to do here is I will do numbers 1, 3 and 5, and we will do this one in class, and we will do this one in class as well. So the first one is the integral of 1 over x squared minus 5, and we know from the list that we're going to have some square root business in here. So if we rewrite it as x squared minus the square root of 5 squared, then we can find it in the list. Alright, so what we're doing is we're forcing what we've got to fit a pattern. Then it's straightforward from the list. It's 1 over 2 root 5 times the natural log of x minus root 5 over x plus root 5 plus c. The third one on the list there, again, we just have to force it to fit a pattern. So it's 1 over x squared plus 4x plus 2. And by completing the square, we can rewrite it as x plus 2 squared minus 2. Some of you may need to go over completing the square. Just look it up in the index. Now, once it's in this format here, we can say, okay, if I have it as that bit squared minus the square root of 2 squared, then I'm right, I can find that sort of one in the pattern, and it will be 1 over 2 root 2 times the natural log of x plus 2 minus root 2 over x plus 2 plus root 2 plus c. So you're forcing it into a pattern, then you're finding the pattern in the list. So let's have a look at the fifth one there. If we take out a fraction, a factor of a fifth to start off with, you can rewrite that as a fifth times 1 over, because we've got to get rid of that 5, so we could rewrite it as now 1 over x squared minus 2 over 5x minus 4 over 5 dx. And again, if we force it into the pattern, it would be a fifth times the integral of 1 over, complete the square again, x minus a fifth squared minus 4/5 plus 1 over 5 squared, sorry, minus 1 over 5 squared, which is 1 over 25. And we can force that into the pattern. And once we've got it into the pattern, then it's just recognize it. So let's just finish this off. So we've got our one thing squared minus another thing squared Now we're right, it's matching the pattern, and we can just now painting by numbers effectively. So the 1 over 5 stays, 1 over 2 times 1 over root 21 over 5 times natural log, oh I hope I don't run out of space, x minus, oops, that fifth fell off there, x minus a fifth plus 21 square root over 5 divided by x minus a fifth minus root 21 over 5 plus c. Oops, that's not quite right. That should be a minus on the top line and a plus on the bottom line. Okay, so all of these are following the earlier one on slide a couple back, the first in the example, so where we've got that the integral of 1 over x squared minus a squared, that's the pattern that we're looking at for these ones here. If you look at all of these ones, they're going to be of the pattern of the third one on slide 8. If we look at the first one, we can easily see that that's equal to 1 over x squared plus 4 squared, and just using the pattern, that's a quarter of tan inverse, it's not behaving itself, tan inverse of x over 4 plus c. The second one we can rewrite using completing the square. We can add 25, subtract 25, so that we can rewrite it as the integral of x plus 5 squared plus the square root of 5 squared, and then straight away we can see that it fits the pattern 1 over root 5 inverse tan of x plus 5 over root 5 plus c, and we'll do this next one in class. For these ones you'll see that they match the patterns on slide 9. So for the first one we can rewrite it as 1 over the square root of 5 squared minus x squared. Now it looks like the pattern, so we can just follow the pattern and say that the integral of that is the inverse sine of x over 5. And for the second one, again, we just have to do a little bit of fiddling. We can rewrite it as 1 over the square root of 3 minus x plus 1 squared plus 1, which we can then further refine as 1 over the square root of 4, because 3 plus 1 is 4, minus x plus 1 squared. See, what we've done now is we've forced it into the pattern. Now we can say, well, okay, that's just going to be the inverse sine of x plus 1 over 2. So we've forced it into the right pattern. So we just follow the list. I'll do the third one in class. Again, it's a matter of what does it look like, find it in the list, and we're done. So this one we could rewrite as 1 over the square root of x squared plus 2 squared, which will be inverse sinh of x over 2 plus c. The second one we have to do a little bit of jiggling first but we can rewrite it as the square root of x plus 5 over 2 squared plus 23 over 4. That's just by completing the square. And a little bit of further jiggling, we can see that that's equal to 1 over the square root of x plus 5 over 2 squared plus the square root of 23 over 4, which would be root 23 over 2 squared. So all we're doing is we're just fiddling to make it fit the pattern, and now it does. So the integral of that would be inverse sinh of x plus 5 over 2 over root 23 over 2, which we could further rearrange and put the 2 up the top. Plus c plus c. So I'll do the next one, the third one, in class. Find the pattern, match it up, and we're done. For the first one, easily recognise that that's x squared minus 3 squared, the square root of x squared minus 3 squared. And follow the pattern, inverse hyperbolic cos of x over 3. The next one's a little bit more difficult. We have to jiggle it a little bit first, complete the square, and collect it all up, and then we'd see that that just becomes the integral of the square root of. Now the first bit of it would be x plus 3 squared minus 8, and that would become the integral of square root of x plus 3 squared minus the square root of 8 squared. And again, it's just an inverse cosh one of x plus 3 over the square root of 8, which is 2 root 2. There are two ways to do this, as there often are. There's going to be a calculus way, and we'll do that in class, but there's also a non-calculus way, and we'll do that here. There's just a formula that says the volume of a hemisphere is pi h over 6 times 3r squared plus h squared, and if we work from the diagram, we can see that that's pi h over 6 times 3 times, now the radius, just using Pythagoras, will be 1 minus h times h, and h squared is still going to be h squared, and a little bit of algebra there, 3h minus 3h squared plus h squared, which is pi over 6, sorry, pi h over 6 times 3h minus 2h squared, and if we throw in 1000 for good measure, then we get the answer that we're looking for. Excuse me. So we're now going to start using integration, and the first thing that we're going to do, or that we need to know before we can use it, is how to find what's called a definite integral. This kind of thing is what's called an indefinite integral. But when we put in limits, as we have here a and b, then it becomes the definite integral. And all we have to do is find the integral and substitute in 3, or the top limit in this case 3, bottom limit 1, and then subtract. So the integral of x squared would be x cubed over 3, and we need to do that between 3 and 1. Now, I could, let's just go back and undo that. I could, if I was being really particular, put plus c in there and then find my limits. But what we'll actually find is we substitute in 3, so that would be 3 cubed over 3 plus c minus 1 cubed over 3 plus c, and the c's disappeared, so we end up with 8 2/3. We don't need to have the c, because c minus c goes. Now, if you're the sort of person that thinks, oh, I need to put it in because if I don't put it in this time I'll forget, that's fine. It's fine to put it in there. I tend not to, because I know that it's going to disappear, and what I would say would be directly this. Do the arithmetic. And I do it that way. But if you like, you can put the c in each bracket, subtract it, and it's all gone, if that feels safer for you. Sometimes, as I keep trying to impress upon you, sometimes you have to be a bit sneaky to make something fit onto the list, and there's no rule, see this, do that. We have to fiddle around to get it how we want. Sometimes we have to do some crazy substitutions. Here's a crazy substitution. Let's start off by saying, and it looks a bit odd, x equals, well, yeah, x plus 1 minus 1. Let's see how that's going to help us, because remember, not only do we have to do the integration, that we then have to substitute in 3 and 2. So we've got a long way to go before we actually get there. So on the top line now, we've got x plus 1 minus 1 over the square root of x plus 1. And still keeping in the fact that we're doing the definite integrals, we can split this into two fractions. We can say that it's equal to the integral of x plus 1 over the square root of x plus 1 minus the integral between 3 and 2 of 1 over the square root of x plus 1. And then it becomes a whole lot more straightforward. Using algebra, we can get rid of the x plus 1 over root x plus 1 to just simply be root x plus 1. And we can rewrite the second term as x plus 1 to the negative a half. And then they're straightforward to integrate. We could put them back into one term now, since it's all between 3 and 2. The integral of x plus 1 to the half would be x plus 1 to the power of 3 over 2 over 3 over 2, which would become 2 over 3, minus x plus 1 to the power of 1 over 2 over 1 over 2, which would become 2, and using your calculators that would become 4 over 3. Again, this one is a little bit tricky. Let's make the same substitution, slightly rejigged this time. Let's make a substitution where x is equal to x minus 1 plus 1. So now our integral becomes still between 1 and 0, but x minus 1 times x minus 1 to the power of 11 plus the integral between 1 and 0, 1 and 0 of 1 times x minus 1 to the power of 11. So I've split it up. There's my first term going into there, and there's the second part of that that's going into there. And the first one can now be simplified as x minus 1 to the power of 11, and the second term can be simplified to x minus 1, the first one should have been x minus 1 to the power of 11 plus 1, which would be 12, and this one stays as 11. So now it's really simple. It's x minus 1 to the power of 13 over 13 plus x minus 1 to the power of 12 over 12, and we're going to substitute in 1, substitute in 0, and subtract, and we should get 1 over 13 minus 1 over 12, which is negative 156ths. At the start, remember, I talked about using integration to find the area by taking smaller and smaller and smaller pieces, and you can look here. Here's the example where it's a square. That's kind of trite, but we could take rectangles that would underestimate, or we could take rectangles that would overestimate. Either way, if we took our rectangles as being smaller and smaller and smaller and smaller and smaller and smaller, and then use the idea of integration as being a sum in a limit, then we can use integration to find an area underneath a curve. The formal proof would be done as on this slide, so that the area under a curve between A and B would be the limit as delta x goes to 0 of all these little rectangles added up, but we can just use that and not worry about the first principles idea. One important fact to notice is that the integral between A and B is equal to the negative of the integral between B and A, and the fact that we can split integrals up. So if we're looking at from A to B, and we can break that up into A to C and then C to B, just as you would expect. Now let's have a look at the first of these problems, where you're asked to find the area between -1 and 2 under the curve y equals absolute value of x. Now remember that the absolute value of x is equal to the value of x if x is greater than or equal to 0, and the opposite of x if x is less than 0. So have a look at the diagram. The part of it is negative between, x is negative between 0 and -1, so that's one part of our graph, and then our other part of the graph is where x is positive between 0 and 2. So bearing the definition in mind, we can split this first one into being the integral between 0 and 1 of the absolute value of x plus the integral between 0 and 2, and then using the definition that between 0 and 1 it's negative, so that becomes the integral between 0 and 1 of negative x dx, and the right hand part is fine because it's positive. And following on, the integral of negative x would be negative 1/2 x squared. We're going to find that between 0 and 1, and this one would be just the integral of x squared between 2 and 0. And use your calculator. And because we're finding area this time, you have to have a unit. And I'll do this next one in class. Here we're trying to find areas under trig curves. I'll do the second one in class, so I'll do the first one here. Now we've got to find the area of the function under the sine curve between 0 and 2 pi. Let's look at the sine curve between 0 and 2 pi. Now the rule says that everything's fine where we're looking at the area above the curve. Above the curve is between 0 and pi, and below the curve it's between pi and 2 pi. So to deal with this bit, we take the absolute value of the integral, and that flicks it into being a positive number. So we can split our integral to find the area. It's going to be the integral between 0 and pi. That's fine. And then we're going to add the absolute value of the integral between pi and 2 pi. Okay, the integral of sine is negative cosine. And the same for the next one, only taking the absolute value of it. Now make sure your calculator's in radians, because we're doing calculus. So the first one would be 2, and the second one would be the absolute value of negative 2. Which would give us 4 square units. On the last slide, let's just do a review. The first one, it's just every one of those 3 terms is on the list. So we just go through it term by term. The integral of the first one would be 5x to the 4 over 4 plus x squared over 2 times the 3 that's out the front, and the integral of 4 over x would be 4 natural log. Now if we're being really picky, we put absolutely there. I tend not to, because I know that it has to be positive, but if you're going to be picky, put in the absolute value one there. Second one, looks a bit tricky. No, why don't we multiply it out first, and then we can integrate after that. So we could integrate it and split it into 2 terms. It would be 3 times root x minus the integral of x root x, which would be 3 times the integral of x to the half minus the integral of x to the 3 over 2, at which stage it becomes quite straightforward. The first term would be 3 times, what would it be? It would be x to the 3 over 2 over 3 over 2, so times 2 over 3 minus x to the power of 5 over 2 over 5 over 2, so it would be times 2 over 5, and cancel that, and don't forget to add c. The next one, we can split it up. We can split it up by doing the division before we start. So x is into x plus 1 would be 1. That would be x. Do the subtraction. 1. X is into 1. No, so it has to be 1 over x. So we're just doing algebra first, and then we could say that the integral of x plus 1 over x is the integral of 1 plus the integral of 1 over x dx. So the integral of 1 would be x, and the integral of 1 over x would be natural log of x. The fourth one there, that's one that's going to fit a pattern. 9 squared is equal to 3 squared, so it's equal, the pattern would fit the cosh inverse, so we can go straight to that. It would be cosh inverse of x over the square root of 9, which is 3. And that's just straight from the list.